To determine if there will be sufficient power to each light, we need to calculate the voltage drop. The voltage drop formula is voltage drop in volts equals current in amps times distance in feet, all multiplied by resistance per foot of wire in ohms per foot. Let's look at some assumptions. The load is 720 watts spaced out. There are lights consuming 18 watts each. The number of lights is therefore 720 watts divided by 18 watts, totaling 40 lights. The wire is 10 American wire gauge stranded low voltage underground wire. The distance is 500 feet out and back. For 10 American wire gauge stranded low voltage underground wire, the resistance is approximately 0.53 ohms per foot. Current equals load in watts divided by voltage in volts. Assuming a 12 volts transformer, the current equals 720 watts divided by 12 volts, totaling 60 amps. Voltage drop in volts equals 60 amps times 500 feet, multiplied by 0.53 ohms per foot, which equals 159 volts. With a transformer voltage of 12 volts and a voltage drop of 159 volts, the voltage at the lights would be 12 volts minus 159 volts, totaling minus 147 volts. The voltage at the lights would be negative, indicating that there is not enough voltage to power the lights. Running the wire in a loop does not prevent voltage drop. To have sufficient power, you would need to use a thicker wire, such as 6 American wire gauge or 4 American wire gauge, or increase the transformer voltage to compensate for the voltage drop. Let's look at transformer options. Firstly, multi-tap transformers. These transformers have multiple taps at different voltage levels, allowing you to select the appropriate voltage to compensate for voltage drop. However, it is rare to find a 900 watts multi-tap transformer with a single set of posts. Secondly, boost transformers. These transformers increase the voltage output beyond the input voltage, which can compensate for voltage drop. However, they are typically more expensive and less efficient than multi-tap transformers. Given the high load and the need for a single post transformer, it is recommended to use a 6 American wire gauge or 4 American wire gauge wire and select a transformer with the appropriate output voltage to compensate for the voltage drop. It is crucial to accurately calculate voltage drop to ensure proper performance and longevity of your low voltage lighting system. Understanding the factors that contribute to voltage drop, such as wire gauge, distance, and load, allows you to make informed decisions when selecting components and designing your system. Using a thicker wire with a lower resistance per foot reduces voltage drop significantly. For example, switching from 10 American wire gauge to 6 American wire gauge or 4 American wire gauge will decrease the resistance and improve voltage delivery to the lights. You can consult the National Electrical Code, section 310.15, for ampacity tables to ensure the selected wire gauge can handle the current load safely. Increasing the transformer voltage can also compensate for voltage drop. Multi-tap transformers provide flexibility by allowing you to choose the appropriate voltage level based on the load and distance. Boost transformers can also be used to increase the voltage, but they are generally less efficient and more expensive. When selecting a transformer, consider the total load of the lighting system and choose a transformer with sufficient capacity. It's always better to select a transformer with a slightly higher capacity to account for future expansion or increased load. Proper wiring techniques are also essential to minimize voltage drop. Ensure all connections are tight and secure to reduce resistance. Use waterproof connectors to prevent corrosion and maintain a reliable electrical connection. Additionally, avoid excessive bending or kinking of the wires, as this can increase resistance and lead to voltage drop. When spacing the lights along the run, try to distribute the load evenly to minimize voltage drop. Unevenly distributed loads can cause some lights to receive less voltage than others, resulting in inconsistent brightness. Consider using a voltage meter to measure the voltage at different points along the run to identify areas with significant voltage drop. This can help you pinpoint wiring issues or load imbalances. Regular maintenance is also essential to ensure the long-term performance of your low-voltage lighting system. Inspect the wiring, connectors, and transformer regularly for any signs of damage or corrosion. Replace any damaged components promptly to prevent further issues. In summary, calculating voltage drop is crucial for designing and maintaining a reliable low-voltage lighting system. By understanding the factors that contribute to voltage drop and implementing appropriate solutions, you can ensure that all lights receive sufficient voltage and operate at their optimal brightness. Selecting the right wire gauge, transformer voltage, and wiring techniques are essential for minimizing voltage drop and maximizing the performance of your lighting system. Remember to consult the National Electrical Code and other relevant resources for guidance on safe wiring practices and component selection. By following these guidelines, you can create a beautiful and functional low-voltage lighting system that will provide years of reliable service. The voltage drop calculation, as previously described, plays a pivotal role in electrical system design, particularly in low-voltage applications like landscape lighting. The formula voltage drop equals current times distance times resistance provides a quantifiable method for assessing potential voltage losses across a conductor. This calculation is not merely an academic exercise, but a practical necessity for ensuring the efficient and safe operation of electrical devices. The current, measured in amps, represents the flow of electrical charge through the wire. The higher the current, the greater the potential for voltage drop. This is because the resistance of the wire impedes the flow of current, causing some of the electrical energy to be dissipated as heat. The distance, measured in feet, is the length of the wire run. The longer the wire, the greater the resistance and the potential for voltage drop. This is simply because the current has to travel a longer distance, encountering more resistance along the way. The resistance per foot of wire, measured in ohms per foot, is a property of the wire itself. Different wire gauges and materials have different resistances. Thicker wires have lower resistance than thinner wires, and copper has lower resistance than aluminum. As noted earlier, for 10 American wire gauge stranded low voltage underground wire, the resistance is approximately 0.53 ohms per foot. This value is crucial for accurate voltage drop calculations. The selection of an appropriate transformer voltage is also critical. The transformer steps down the higher voltage from the electrical grid to a lower voltage suitable for the lighting fixtures. In the example, a 12 volts transformer was assumed. However, depending on the load and distance, a higher voltage transformer might be necessary to compensate for voltage drop. The 720 watts load, distributed among 40 lights each consuming 18 watts, represents a significant electrical demand. This load draws a substantial current, which exacerbates the voltage drop issue. The calculated voltage drop of 159 volts far exceeds the available 12 volts from the transformer, resulting in a negative voltage at the lights, indicating a complete failure of the system. The solution lies in reducing the voltage drop by either decreasing the resistance of the wire or increasing the transformer voltage, or a combination of both. As suggested, using a thicker wire, such as 6 American wire gauge or 4 American wire gauge, would significantly reduce the resistance and the resulting voltage drop. Alternatively, a multi-tap transformer could be used to provide a higher voltage, compensating for the voltage lost along the wire run. Multi-tap transformers offer the flexibility of selecting the appropriate voltage level based on the specific requirements of the lighting system. Boost transformers, while also capable of increasing voltage, are generally less efficient and more expensive than multi-tap transformers. Therefore, they are typically not the preferred solution for voltage drop issues. In addition to selecting the appropriate components, proper wiring techniques are essential for minimizing voltage drop. Ensuring tight and secure connections, using waterproof connectors, and avoiding excessive bending or kinking of the wires all contribute to reducing resistance and improving the overall performance of the lighting system. Regular maintenance is also crucial for ensuring the long-term reliability of the system. Inspecting the wiring, connectors, and transformer for any signs of damage or corrosion, and replacing any damaged components promptly can prevent potential problems and ensure that the system continues to operate efficiently. In conclusion, understanding voltage drop and implementing appropriate mitigation strategies are essential for designing and maintaining a successful low-voltage lighting system. By carefully considering the factors that contribute to voltage drop, selecting the right components, and employing proper wiring techniques, you can ensure that all lights receive sufficient voltage and operate at their optimal brightness, providing a beautiful and functional lighting solution. Now, let's delve deeper into the practical aspects of selecting the right wire gauge for a low-voltage lighting system, focusing on the impact of different gauges on voltage drop and overall system performance. As previously discussed, the wire gauge plays a crucial role in determining the resistance of the wire, which directly affects the voltage drop. Thicker wires have lower resistance, allowing more current to flow with less voltage loss. The American wire gauge, abbreviated as AWG, is a standardized system for denoting wire sizes. The smaller the AWG number, the thicker the wire and the lower its resistance. For example, 4 American wire gauge wire is thicker and has lower resistance than 10 American wire gauge wire. When selecting the appropriate wire gauge, it is essential to consider the current carrying capacity of the wire. The National Electrical Code, Section 310.15, provides ampacity tables that specify the maximum current a wire can safely carry without overheating. Exceeding the ampacity rating of a wire can lead to insulation damage, fire hazards, and system failure. Therefore, it is crucial to choose a wire gauge that can handle the expected current load with a safety margin. In the example provided, the load is 720 watts and the assumed voltage is 12 volts, resulting in a current of 60 amps. According to the National Electrical Code, 10 American wire gauge wire has an ampacity of approximately 30 amps, which is significantly less than the required 60 amps. This indicates that 10 American wire gauge wire is not suitable for this application and a thicker wire gauge is necessary. 6 American wire gauge wire has an ampacity of approximately 55 amps, which is still slightly below the required 60 amps. However, 4 American wire gauge wire has an ampacity of approximately 70 amps, which provides a sufficient safety margin. Therefore, 4 American wire gauge wire would be a more appropriate choice for this application. In addition to the ampacity rating, it is also important to consider the voltage drop when selecting the wire gauge. As previously calculated, 10 American wire gauge wire would result in a significant voltage drop of 159 volts, which is unacceptable. Using 4 American wire gauge wire would significantly reduce the voltage drop due to its lower resistance. To accurately calculate the voltage drop for different wire gauges, you can use the voltage drop formula mentioned earlier. You will need to know the resistance per foot of the wire gauge you are considering. This information can be found in electrical engineering handbooks or online resources. Once you have the resistance per foot, you can plug it into the formula along with the current and distance to calculate the voltage drop. It is generally recommended to keep the voltage drop below 3% for lighting circuits and below 5% for power circuits. Exceeding these limits can lead to dimming lights, reduced equipment performance, and increased energy consumption. In summary, selecting the right wire gauge is a critical step in designing a low-voltage lighting system. It is essential to consider both the ampacity rating and the voltage drop when making this decision. Choosing a wire gauge that can handle the expected current load with a safety margin and keeping the voltage drop within acceptable limits will ensure the efficient and safe operation of the lighting system. Remember to consult the National Electrical Code and other relevant resources for guidance on safe wiring practices and component selection. By following these guidelines, you can create a reliable and high-performing low-voltage lighting system. Now, let's transition to a more in-depth exploration of transformers in low-voltage lighting systems, focusing on multi-tap and boost transformers, their characteristics, and their appropriate applications. Transformers are essential components in low-voltage lighting systems as they step down the high voltage from the electrical grid to a lower voltage suitable for the lighting fixtures. The transformer's primary function is to provide a safe and efficient voltage level for the lights, ensuring their proper operation and extending their lifespan. There are different types of transformers available, each with its own advantages and disadvantages. Multi-tap transformers are a popular choice for low-voltage lighting systems due to their flexibility and ability to compensate for voltage drop. These transformers have multiple taps at different voltage levels, allowing you to select the appropriate voltage to match the load and distance requirements of the lighting system. For example, a multi-tap transformer might have taps at 12 volts, 13 volts, 14 volts, and 15 volts. If you are experiencing voltage drop issues, you can select a higher voltage tap to compensate for the voltage loss along the wire run. Multi-tap transformers are particularly useful in situations where the load is unevenly distributed or the distance between the transformer and the lights varies significantly. By selecting the appropriate voltage tap for each section of the lighting system, you can ensure that all lights receive sufficient voltage and operate at their optimal brightness. Boost transformers, also known as step-up transformers, are another type of transformer that can be used in low-voltage lighting systems. These transformers increase the voltage output beyond the input voltage. For example, a boost transformer might take a 120 volts input and output 240 volts. Boost transformers can be used to compensate for voltage drop in long wire runs or in situations where the load is particularly high. However, boost transformers are generally less efficient and more expensive than multi-tap transformers. They also tend to generate more heat, which can reduce their lifespan. Therefore, boost transformers are typically not the preferred solution for voltage drop issues unless there are specific circumstances that warrant their use. When selecting a transformer for a low-voltage lighting system, it is essential to consider the total load of the system. The transformer's capacity should be sufficient to handle the total wattage of all the lights connected to it, with a safety margin. It is generally recommended to select a transformer with a capacity that is 20% to 25% higher than the total wattage of the lights. This will ensure that the transformer is not overloaded and will operate efficiently. In addition to the load capacity, it is also important to consider the transformer's voltage rating. The transformer's output voltage should match the voltage requirements of the lighting fixtures. Using a transformer with an incorrect voltage rating can damage the lights or reduce their lifespan. When installing a transformer, it is essential to follow the manufacturer's instructions carefully. The transformer should be mounted in a well-ventilated location to prevent overheating. The wiring connections should be tight and secure to ensure a reliable electrical connection. In summary, transformers are essential components in low-voltage lighting systems, providing a safe and efficient voltage level for the lights. Multi-tap transformers are a popular choice due to their flexibility and ability to compensate for voltage drop. Boost transformers can also be used, but they are generally less efficient and more expensive. When selecting a transformer, it is essential to consider the total load of the system, the voltage rating of the lights, and the manufacturer's instructions. By following these guidelines, you can ensure that your low-voltage lighting system operates efficiently and reliably. Now, let's discuss some advanced strategies for managing voltage drop in complex low-voltage lighting systems, including techniques for optimizing wire routing, load balancing, and voltage monitoring. In complex low-voltage lighting systems, where there are numerous lights, long wire runs, and unevenly distributed loads, managing voltage drop can be a significant challenge. In these situations, it is essential to employ advanced strategies to minimize voltage loss and ensure that all lights receive sufficient voltage. One effective strategy is to optimize the wire routing. Instead of running a single long wire from the transformer to the last light in the system, consider dividing the system into multiple zones or circuits. Each zone can be powered by a separate wire run from the transformer, reducing the overall length of each wire run and minimizing voltage drop. Another strategy is to balance the load across the different zones or circuits. Try to distribute the lights evenly across the zones so that each zone has a similar load. This will prevent any one zone from drawing excessive current and experiencing significant voltage drop. In situations where the load cannot be evenly distributed, consider using different wire gauges for different zones. Use thicker wire gauges for zones with higher loads and longer wire runs, and thinner wire gauges for zones with lower loads and shorter wire runs. This will help to equalize the voltage drop across the different zones. Voltage monitoring is another important strategy for managing voltage drop in complex low-voltage lighting systems. Use a voltage meter to measure the voltage at different points along the wire runs, particularly at the end of each zone or circuit. This will allow you to identify areas where the voltage is dropping below acceptable levels. If you find areas with significant voltage drop, you can take corrective action, such as increasing the wire gauge, adding a multi-tap transformer, or redistributing the load. In some cases, it may be necessary to use a combination of these strategies to effectively manage voltage drop. For example, you might optimize the wire routing, balance the load, and use different wire gauges for different zones, while also monitoring the voltage at various points in the system. In addition to these strategies, it is also important to consider the environmental factors that can affect voltage drop. For example, temperature can affect the resistance of the wire, which can in turn affect voltage drop. High temperatures can increase the resistance of the wire, leading to increased voltage drop. Therefore, it is important to protect the wiring from extreme temperatures such as direct sunlight or heat sources. In underground installations, it is important to use waterproof connectors and bury the wiring at a sufficient depth to protect it from moisture and physical damage. Moisture can corrode the wiring, increasing its resistance and leading to voltage drop. Physical damage can also damage the wiring, reducing its current carrying capacity and increasing voltage drop. In summary, managing voltage drop in complex low-voltage lighting systems requires a combination of advanced strategies, including optimizing wire routing, balancing the load, using different wire gauges for different zones, monitoring the voltage, and considering environmental factors. By implementing these strategies, you can minimize voltage loss and ensure that all lights receive sufficient voltage, resulting in a reliable and high-performing lighting system.